The reason I bring those up is because if we're looking at computational burden, we have this issue of how many contingencies should we use. So this is looking at running this over and over and over again and seeing how does our expectation converge over time. So each one of these lines is another run of a random set of 1,000 n-1s. And if we do that, we can see that we're pretty happy that with 1,000, we've pretty much converged on the actual expectation. This is the plot for the expectation. We do this for the CVAR as well. With CVAR, it takes a little longer to converge because you're converging on a tail, right, as opposed to converging on the average value. But by the time we get to 1,000, we're quite happy. The problem we have is that with the 2,000 bus network, we're not converged yet. So I'm showing you these results, and these results are one of these lines. And actually, if you look at 1,000, there's a pretty big range of what that expectation could be. So by the time we've run 1,000 simulations of n-2s on the 2,000 bus network, really, I have, say, confidence that my expectation is somewhere between about 1,200 and 2,400 or something like that. So it's nowhere near converged to a final answer. And if we look at the CVAR values, that's going to be even worse. So the amount of burden that we have, the amount that we need to run in order to get this to a reasonable solution, that's a real challenge. Things we can do to help with that, we can do things like increasing step size. So at the moment, you take a dynamic simulator, and by default, you're probably running at about 10 milliseconds. Like that's a kind of typical thing that we do for most power system dynamics. You can obviously push this up. You can't push it too far because at some point you're pushing it to a stage where it's not fast enough to see the devices that you're tripping. So if you've got a fast rate of change in frequency, you can't go much faster than this, than about 0.3 seconds, because your rate of change of you might have crossed over a couple of thresholds for under frequency load shedding within 0.3 seconds. So you need enough resolution in your time step to be able to take an action before the next time step would occur. But if we do this and we look at what the results we get out, so expectation is fine up until about 0.2 and then starts to crumble a little. And then the tail values are actually probably slightly more consistent even than the expectation is. So here we're seeing that the tail is surprisingly consistent as we increase the step size. And so similar for the actual kind of average number of line outages across all the different cases. So if we take all of these different plots, and this is last one simulation time, which you can just about see. So we've got about 20 hours there down to about 12 hours here. So it's not a case that you do a 30 times increase in step size and it's 30 times faster. No, it's about 40% faster, something like that. So you get a benefit, but it's still slow. So this is why when we need to push that to tens of thousands of simulations, it's a bit of a challenge. We tend to stick somewhere in this space just because it's kind of an average of computational burden and accuracy.